Hi, I'm Antonio Sala, and in this video we'll show how Matlab's symbolic toolbox can solve a linear ordinary differential equation. We'll use the well-known mass spring damper, which appears in most introductory textbooks to system dynamics. Our problem to analyze would be computing the evolution of this spring with some damping by friction with walls and spring losses, and assuming that the equilibrium position is 0 in here. If it's not 0, we can just translate the origin of our coordinate reference system, so there is no loss of generality. And if we assume that friction is somehow linear, then we have this ordinary differential equation governing the movement of the red mass. Mass times acceleration, second derivative of its position, y of t, equal to resulting force with a spring component proportional to the deviation and the friction component proportional to speed. How do we encode this differential equation into the symbolic toolbox of Matlab? Well, we will create a symbolic function of time with this line. This line will create symbolic constants, the constant parameters in my model, mass, spring constant, and friction constant. And for convenience, we will denote as vel, velocity, first derivative of function y, and this acceleration, second derivative of function y. So this thing is the ordinary differential equation in here translated into Matlab syntax. Of course, I could also have written here directly the diff2 and the diff expression here, but in this way we are sort of closer to the physical intuition that led us to this equation. Anyway, we have the differential equation as a Matlab symbolic toolbox object, ODE sim, which is this one. Here we have it written in a pretty format. We do wish to solve and compute actual movements of the spring. I mean, our final goal is obtaining the formula of this movement. So we are going to replace our constant parameters by given numbers. So we will have here numerical values of mass, and spring and damping constants, and I substitute the symbolic variables here by the numerical values. So this is the actual differential equation to solve once the constants have been substituted by the actual numerical values. The command that actually solves differential equations in symbolic toolbox is the dsolve command. You may look at Matlab's documentation for details on what this command does and how it's used. Anyway, here we just give the command this ODE, and, well, the solution it provides is this thing here, some exponentials and trigonometrical functions. Why it's so, it's a matter of a theoretical material we are not discussing here. Anyway, importantly, we have two constants because this differential equation has infinitely many solutions. All movements of the spring and mass fulfill these equations, but depending on the initial position and speed, the actual formula for the movement will be different. So theory tells us that giving suitable values to C1 and C2, we will encompass all possible spring movements when there is no forcing input. I mean, this is a free response. I am not exerting any force on the red mass. Okay, in this formula, the coefficients in the exponential in here, 1/5, that's called the decay rate, and 7/5 is called the oscillation frequency of the free response in radians per second. Of course, if this is the solution of the position y, the velocity will be its derivative, which, taking diff and trying to do some simplifications, ends up being this according to Matlab's symbolic toolbox. So, does this thing actually verify the ordinary differential equation in here? Of course it does. If I tell Matlab to check whether the mass times the second derivative of the solution is equal to this right-hand side of the ODE, then of course Matlab tells me that it's true. It verifies the equation. Of course it's a solution, but okay, this is kind of an explicit check that this equality is indeed true. The initial position would be obtained substituting t by 0 in here, and the initial speed would be obtained substituting t by 0 in this expression below. So initial position is c1, initial speed is this thing. So, as usual, in ODE solving, if, for instance, I want to simulate the spring when initial position is 3 and initial speed is 2, I can compute C1 and C2 by solving this system of two linear equations. But actually, I do not need to explicitly do that because, okay, symbolic toolbox can indeed do it. So this expression is called the general solution. All the spring movements have this expression. And when I fix initial position and speed, then I get a particular solution fitting these initial conditions, and dsolve computes the suitable values of C1 and C2. So I get this expression for the spring position. And of course, if we replace t by 0, then this will be 1, this will be 1, and this will be 0. And making operations, we can indeed check that the initial position when time is 0 is 3. And if I take the derivatives of the position, this would be the speed. And of course, if I substitute in this velocity time by the number 0, then I get 2 as required. In my problem statement, here we have position, and here we have velocity. So that's it. The only remaining thing would be, let's say, plotting set position with the command fplot. Plotting a function of the symbolic toolbox is carried out with function plot, fplot, and same for speed. And then speed is the dashed red line, position is the thick blue line, and here we have the so-called time response from initial position equal 3, initial speed equal 2. This is a function plot. Of course, it's kind of easier for us to interpret what we are doing if we see an animation from an initial position in here, and then, as this is a stable system, it dissipates energy. It will oscillate until it stops at the equilibrium position equal to 0, when a lot of time has elapsed. So this is kind of the animation view of the solution we have obtained. For brevity, I will discuss in a separate video which is the Matlab code to execute this animation. Nevertheless, that would be just Matlab programming with drawing functions, but all the important conceptual stuff general solution, initial conditions, and differential equation solving has actually been discussed in this video. We finish with this. Thanks for watching.